In this video, we'll be discussing the important topics of first module. So if you have not watched my previous video, I have explained all the module-wise important questions there. So as an extension to that, I'll be discussing the answers here. So starting from the first module, it's basically, first module has majority of theoretical topics, and we have only two, three algorithms here, that's it. And based on those algorithms, you can expect problems, but then majorly it's theory only. So it's a pretty easy and scoring module, I would say. First is definition of AI. So development of computer systems capable of performing tasks that typically require human intelligence is said as artificial intelligence. So these tasks could be learning, reasoning, problem solving, understanding, natural language processing, and so on. So we have to write the textbook definition here. So that is, Scaffold in 1990 stated that a field of study that seeks to explain and enumerate behavior or intelligence behavior in terms of computation processes. So we need to write this or this. Rich and Knight in 1991 stated that study of how to make computer do thing that which at moment humans are better at. So this was the definition of AI which they gave. So if they ask definition of AI, one general definition, and any out of these two, any one you can write. Then we have the applications. So in applications, healthcare, gaming, finance, data security, social, and all of these, I need not explain it further because you can write the applications. You can write anything in this, but then make sure that you cover these points. Then in foundations of AI, we have these. So first is philosophy. So it raises fundamental questions about consciousness, ethics, nature of intelligence, etc. And then coming to mathematics, we have all the math topics are important, right? Like algebra, calculus, discrete mathematics, and all. Coming to economics, we make use of statistics in AI. So that economics is also a basic foundation of AI. Then we have neuroscience. So in neuroscience, we make use of the neural networks. So to solve the complex, to create the complex models, we make use of neural networks, right? So that is derived from neural science. Then we have psychology. In psychology, understanding of human behavior and then perception influencing the development and all is done in psychology. Then we have computer engineering. So all the hardware and software parts are taken care here. Here we have the control theory and cybernetics. So that is principles for designing that could regulate themselves, influencing the development of autonomous AI systems and all. And then in linguistics, we have the natural language processing. So this was about applications and foundations. Yeah, let's move on to the next topic. That is problem solving agent. So problem solving agent. The next topic we have is problem solving agents. So understanding the basic definition of agent. Agent could be anything that gathers information from surroundings using the sensors and then takes an action based on obtained info using actuator. So on the one side we have sensor, on the other side we have actuator. So that is what an agent basically means. Problem solving agent is a state where we wish to reach a definite goal from present state to the condition. From the given query to the result is from the present state to the condition, the goal state, right? So problem solving agent is a part of AI which enables several techniques like algorithms, heuristics to solve a problem. So by understanding the problem definition here, so in order to precisely define the problem, we need to define the problem precisely first and then analyze the problem. Out of there could be several sub problems arise. So out of those, we need to select the feasible one. Moving on to the steps performed by the problem solving agent, we have first is the goal formulation. That is the output which you want. You need to decide that by considering the problem. And then after that, there would be many solutions to that problem, right? So selecting the best one is important. So first we formulate such the solution and then execute it. After this, we have several definitions. So these could be asked. So the first one is initial state. So initial state is the starting state or the initial step towards goal. And then we have actions. Action is description of possible actions available to the agent. Then we have transition model. So it describes what each action does. So if you have, this is the start state and this is the reach state. Reaching all these several states, reaching all these several points come under the transition model. From here to here, you are depicting the transition model. Then we have the goal test. So once we determine the goal state, we need to check if this is the goal state or not. So for checking, we perform the goal test. And then we have path cost. So path cost is cost to each path that follows the goal. And then we have the state space. So state space consists of all the possibilities. So out of all the possibilities, we have chosen this path, right? So that's what state space says. And then we have branching factor. So number of successor states that can be generated from given state by applying actions. So this was about the basic definitions. These could be asked for 1 or 2 marks. Yeah, 1 or 2 could be asked. Yeah. Agent algorithm. So this could be asked. So firstly, defining the function, simple problem solving agent. P returns an action. So P is a percept. And then in static we have S, that is the action sequence. So it is initially empty. And then we have state is some description of current world state. And then goal, we take a goal which is empty. And then here we take the problem, formulate the problem. Okay. In the further step, we'll formulate the problem. So firstly, we'll update the state to the current state which we are considering. Okay. State as well as the percept would be taken. Firstly, if the sequence is empty, so if there are no if the input, if the state and the problem is not defined, then firstly we'll define the goal, that is formulate goal for the state, and then problem, that is formulate problem for the state, keeping in mind about the goal. Then we have the sequence is to search for the problem, like how we have seen here. First is goal formulation, problem formulation, and many solutions, right? So this is also similar to that. If sequence is failure, then return null action. So if the sequence, what we have searched is a failure, then return null action. And then here action is the first sequence. So the first move made would be stored in action. And then after this, all the subsequent moves would be stored in the sequence. That is rest of the sequences. And then ultimately we return the action. That was the output, right? Which we wanted by considering a problem and then generating an action or output. So this was about simple problem solving agent. We'll move on to the next topic. That is, we have toy problems here. There are 3 problems majorly. So for each problem, the solution is not defined in the textbook, but then the states, start state, actions, all these 6 points need to be defined. So let's start from the 8 puzzle. So in 8 puzzle, we have 3:3 matrix, 3 rows and 3 columns, movable tiles. So they are numbered from 1 to 8. And then we have a blank tile here in the middle. So the goal is to read from the start state to the final state. This is the goal state which we have. So our task is to convert start state to goal state by sliding tiles. So here we can move only one tile at a time. So here let's define these points. So firstly, the state here is, it tells the location of each tile. So 7 is present at this point. That is, the state defines all of those. Then we have the start state. So start state could be anything. So in order to shift to this point, we can either shift 2, 5, 6 or 3. Any of those could be the start state. And the actions here we performed here, it can move up or down or left or right. Then we have the transition model. That is a given state, action, it returns the resulting state. And then we have the goal test. So we check if the state matched required configuration. So this was the required configuration, right? So at the end, when we reach the goal state, we perform the goal test in order to check if the required goal state and the reached are same or not. The configuration is same or not could be checked from here. And then we have the path cost. So each path costs one unit. Okay. So in order to move each tile, it would cost 1 unit. So this problem can be used for testing new search algorithms in AI. So this was about the 8 puzzle problem. Then we have the vacuum problem here. So here V is represented, V can be considered as vacuum and dot is the dirt. So here we have 2 worlds here, this one and this one, left and right. So in both the worlds, there are dirt is present in both the grids. So we can move, the vacuum can move either this side, or it can shift. So those are the operations of vacuum. So we'll look into the written part here. So the vacuum world consists of an agent, that is the cleaner here, and the dirt present in 2:2 grid, 2 into 2 grid. So it can move or be in any one of those locations, each with or without dirt. So there are 8 possible worlds here, that is n into 2 power n. That is, we have taken 2 slides here, 2 tiles here, right? 2 into 2 power 2. 4 into 2 is 8. That's why we have 8 possible states here. So firstly, we need to determine by the state could be determined by the cleaner location and presence of dirt. And then the start state, it could be any state. And then the actions are left, right, and shift. Shift a lot. It can suck. Okay. Then we have the transition model. So actions have expected effects. And then we have the goal test. Check if all grids are clean without any dirt. And then the path cost is each step costs 1 unit. So looking at this vacuum, the vacuum is here. So it could either move. It could see if it moves right, then we'll be in this configuration. If it moves left, then in this configuration. Next, we have consumes this dirt. Then the dirt would be vanished from here. So we have V here. So from V, it can either move, it can move to the other side, right? So it can shift here. So as we write shift, when we shift, the vacuum comes here, right? And on this side also, the vacuum is here. It has consumed the dirt. Now it can shift this side, right? So if it shifts this side, then the dirt and vacuum would be in the same grid. Now, if the vacuum consumes the dirt, then there would not be any dirt left out here, right? So it will be clear. And even on this side also, it will be clean and right? So these are the final states which we need to obtain. So in exam, if they ask about toy problems and explain a vacuum cleaner problem or 8 puzzle or 8 queens, then we need to define the problem firstly and then write these 6 points. Next, we'll look into the 8 queens. So goal is to place 8 queens on chessboard and no queen should attack each other. So yeah, so the first we'll start with the start state, that is arrangement of chessboard and queens from Q1 to Q8. 1, 2, 3, 4, 5, 6, 7 and 8 queens are taken here. And then we have the initial state, that is no queens on the board. We need to arrange the queens one by one, right? Then we have the action. So add queen to any empty square. And then the transition model is we need to make sure that no queens are being attacked by each other. So if we add first queen here, then we can't add here, here, here. So we can add as the possible position is here. Now if we add the queen 2 here, queen 3 can't be placed here, here, here. So the possible position is here. And accordingly, you need to follow the sequence. Then we have the goal test, that is 8 queens should be there and none of them should be attacked by each other. And then the state space is approx 1.8 into 10 to the power 14 positional sequences could be possible here. So this was about the toy problems. Now we'll look into the algorithms part. So in the searching algorithms, we have uninformed and informed. So in uninformed, we have depth first search, breadth first search and uniform cost search. In informed part, we have greedy best first search and then A star search. So before moving on to these specific searching algorithms, let's look into the general tree search algorithm. So general tree search algorithm is pretty simple. So function, general search, there is a problem and then you define a strategy. It could either result a solution or a failure. So you start from one point, initial a search tree using initial state of problem. You initialize it to one point. And then if there are no candidates for expansion, then the return failure. But then if you have leaf nodes further, then select each one and check if it matches. Suppose this is 1, 2, 3, 4 and 5 and our goal state is 3. So first you select the leaf node and check if matches the goal state or not. If not, then again iterate to the next leaf node. If the node contains goal state, then return solution, else expand node resulting nodes to the search tree. So that's what I have explained it in simpler terms. That's it. Next we have the BFS, that is breadth first search. So in BFS, the algorithm is pretty simple here. So function, here we make use of, in BFS we make use of Q. Okay, so function, BFS, problem, it could either result a solution or return failure. So firstly we take a node and initialize it with a state. So once you initialize the state, we take the initial state and the path cost is 0 starting. Okay, because we are going to define the path cost right later. Then we have if goal state, if problem.goal test of node and state returns the solution, then we have found the solution. So you give the solution back and the program ends there. If not, we make use of a frontier. So frontier is a queue. Okay, the first in first out queue with node as only element. So we take a queue and we write the first element as the input. Now we take another set called empty explode set, which needs to be empty initially. Okay, so firstly we take this particular node and then we explore that node. So from that node, whatever are the further possible child nodes linked to it, we'll write it as it is. Here 2 and 4 I'll write. I took 1 as the first node, right? I'll write 2 and 4 as it is. Now once I have written all the possible routes from 1, I need to transfer from frontier set to the explode set. So as this is a queue, from this side will enter and from this side it needs to be removed or popped out. So in explode set I'll write 1 here firstly. Then we'll consider 2. Okay, so that's what algorithm says. So node is equal to pop frontier. If empty, then frontier results failure. else node is equal to pop frontier, add node dot state to the explode. For each action in problem dot actions node dot state do, that is perform the action. So child is equal to child node, problem node and action is specified here. If child dot state not an explode and frontier, then child dot goal state of child state, then we need to return the particular solution. That is frontier is equal to insert child and frontier. So this was about BFS. Firstly, I'll explain all the algorithms, and then it will be easy to solve the problem. There are no shortcuts in algorithms. We need to remember all these and write it in the proper order. Then we have the UCS algorithm, uniform cost search. So here also the problem would be considered as input, and then we return either a solution or a failure. Initialize a node with the starting node, and then the state as the problem, and then the input state, the initial state, and the path cost is taken as 0. So firstly, we take the frontier node, that is priority queue ordered by path cost. In previous one, we wrote it generally, right? In BFS, we wrote it generally, but then coming to the UCS algorithm, we have path cost being specified here for each node. To traverse from one node to another, the path cost would be specified. So we need to consider those path cost in this topic, in this algorithm. Then we have the explode set, that is E, that is the empty set here. Loop, if empty, then frontier. If the frontier is empty, then return failure. If not, pop frontier. If a problem dot goal test of node state, then return the solution. If you find the solution at that particular point only in that state, then return the solution. If not, after that, add node dot state to the explode set. It's the similar way only. Then child is equal to child node. We define the problem node and action. Then if child state is child dot state is not in explode or frontier, then we update the frontier with inserting the child and frontier. This is the variation from previous algorithm to the UCS algorithm. That is, if child dot state is in frontier with highest path cost, then replace frontier with child. So here, as I said, the path cost would play an important role. So we'll look into this while solving the problem. Then we have the DFS algorithm. So DFS algorithm is easy again. Function, depth first search. You define you give the problem as input, and then it can result return solution or failure. Initialize, here we make use of stack. Here we make use of stacks. Okay. So initialize the stack using initial state of problem. Initialize explode set to be empty. Initially we are taking the explode set to be empty. Then loop, you consider the loop. If stack is empty, then return failure. Pop from, then we choose a leaf node, and then pop that leaf node from the stack. So if node contains goal state, then you have obtained the solution, give the solution. After that, add it to the explode set. If not, explore or expand the chosen node, adding resulting nodes to the stack. Only if node is in frontier, node in frontier or explode set, you keep on repeating this until you reach the goal state. So this was about DFS algorithm. Now we'll look into the problems. So firstly, we have BFS and DFS. We'll start from BFS. BFS means we need to make use of queues. So there'll be a queue, that is the frontier queue, and then we make use of a explode set. So initially, as the algorithm says, consider 1 and then write it in the frontier part, this node in the frontier part, and then explore 1. When we explore 1, we get 2 and 3, right? So write 2 and 3. Now that 1 is completely explode, pop it out from the queue, remove it from the queue, and add it to the explode set. So 1 is being added. Next, I have 2 here. So consider 2. Now from 2, read all the possible states. That is 4 and 5 I have. So I'll write 4 and 5 here. And then once all the possible states are obtained from the 2, pop this and add it to the explode set. 1 is done, 2 is done. Now I'll consider 3 here. So consider 3. From 3 we have 6 and 7. So fill 6 and 7 here. You're filling from this side and removing it from this side because it is a queue. Okay. So from 3 I have filled 6 and 7. From 1 I got 1 and 2 and 3. From 2 I got 4 and 5. From 3 I got 6 and 7. 1 is done, 2 is done. And then now that I have explored 3, put it in the explode set. Now I'll consider 4. Can you expand 4 further? Are there any other nodes possible from 4? No. So write 4 as it is. For 5 also it is the same condition. for 6 also same, for 7 also same. So if you look at this, BFS generally states that we are doing level order traversal. So this is the first level, second level and third level. We are traversing level wise from the first level to the second level and the third level. Here BFS has order of the complexity is odd big O of B to the power D. B is the maximum branching factor and D is the depth here. So that was about BFS. Now we'll look into the DFS part. So for the DFS part, again I need to consider frontier and then explode set, and along with that I'll make use of a stack. Okay. So firstly, so the frontier here is stack. Okay. So firstly, I'll take 1. So I'll pop 4. So 2 is there in the stack. So from to any other possible state, we have 5 here. So I'll write 1, 2 and 5 here. So from 5, is there any other state possible here? No other nodes are possible. So I'll write 4 and then I'll pop 5 also. I'll write 4, 5 in the explode set. Once 5 is done, once 5 is popped, I have 2 here. So from to anything you can write further? No. So pop 2 also. 2 is also popped, put it in the explode set. Now I have 1 here. So in the stack I have 1 here. Now I'll consider this side. I'll write 3 and 7. So 7, can you further, are there any nodes connected to 7? No. Pop it and put it in the explode set. 3, from 3 any other nodes are possible? 6 is possible. So write 6 in the, put 6 on top of stack. Now from 6 any other possible? No. Then pop 6 and then we have 3 here. From 3 any other possible? No. Put 3 here and 1 here. 1 finally. So this was the explode set or the output for BFS. And in DFS, as we consider the stack, we have got this. Okay, DFS is depth first search. We go depth wise, that is like this and then like this and like this. So that was about BFS and DFS. Let's look into this question, the UCS algorithm. So as we have discussed UCS algorithm, we need to consider the path cost, right? So I'll start from A and D is the destination node or the goal node, okay, which I have to reach. So I'll start from A. From A, only one possible, let me write E here. I'll write 10 here and 15 here. So from A, the possible nodes are B, which requires 4 units, and then E, which requires 10 units. So out of these two, I would select B because this is the shortest one. Okay, from B, I have 2 options further, D or C. So from B to C, I have 2, and B to D, let's write it as 7. Okay, I'll write it as 7 here. So between these two, I would select C. Now the D was the result which I had to reach, right? So if you consider from C to D, I have 3 again, and from E to D also I have 15 again. So the path cost from AED would be 10 plus 15, 25. Whereas the path cost of A, B, C and D, A, B, C and D would be 4 plus 2, 6 plus 3, 9. And then the path cost for A, B and D would be 4 plus 7, 11. So I can say that AB, BC and CD would be the optimal path. So this was about UCS algorithm. Then we have this question. Let's find BFS and DFS for this. So I'll solve it normally without considering the frontier nodes and all. So for BFS, it would be first A, first level is done, and the second level I have B and C, and in the third level I have D, E and F. Whereas if I consider DFS, then I'll have A, from A I'll go to B, and from B I'll go to D. Once I reach, if there are no further leaf nodes here, from here I'll consider E, and then I'll go to C, and then from C I'll come to F. Further there's nothing. So this is for BFS and DFS. So if I sum up for first module, the AI questions are important. Firstly, this could be asked for 10 marks. And then the 3 algorithms which I have covered, DFS, BFS and UCS. So here the algorithm plus problem could be asked. So beyond that, they can also ask the toy problems or the definitions. Okay, problem solving agent, that comes under, this comes under problem solving agent only. So first module is pretty easy. I would definitely recommend you to be thorough with first module, second module also. So stay tuned to my channel. I'll be uploading second module important questions also. So if you have any doubts, do let me know in the comments, and subscribe to my channel. Thank you.